Okay, so the final speaker before lunch is Gregor Traven, who will be telling us about machine learning for understanding stellar sources.
Yes, thank you. So in this talk, nice. In this talk, I would like to present a joint effort for a better understanding and characterization of the data sets that we have available now in the large spectroscopic service. And this is just a few of the people that have contributed to this effort in some way or the other, and they all come from our research group at the University of Ljubljana. So in the beginning, I would like to say a few words about stellar spectra, just to introduce the type of data that we have. And then I will talk about the method of choice, t-SNE, in the context of dimensionality reduction. And further on, I will explain how we actually perform our classification of data using t-SNE and another method called dbScan, and of course a tool that we nicknamed t-SNE Explorer. And I will conclude with some outlook to the future. So, stellar spectrum, if stars were like giant spheres at a certain temperature, stellar spectrum would look something like a black body radiation that we see here. So this is light, intensity of light on the y-axis, and then it's split according to the wavelength on the x-axis. So this axis will be either in angstroms or in nanometers, so 10 angstroms equals 1 nanometer. But of course, this is an ideal assumption. However, the true spectra look more like this. We have, of course, observational noise. There's the outstanding features in the spectrum that we call absorption lines. These are due to the light being absorbed in stellar atmospheres due to the presence of different elements. And, of course, a lot of other influences that shape the spectrum. So, for example, the temperature is one of the physical parameters in the stellar atmospheres that can change this shape significantly. So we go from hotter stars at the top to cooler ones at the bottom. We also see the peak of the emission shifting from shorter wavelengths to longer ones. And we see a lot of strong absorption features in the bottom for cool stars, where we have molecules already forming, and they can absorb this, actually what we call absorption bands. They can produce these absorption bands in the spectrum. So temperature is one important parameter. Then amount of heavier elements, so elements heavier than hydrogen or helium, we call all these elements basically metals. So this is a metallicity measure. So we go from metal poor spectra up here to metal rich ones. So again, a lot more of absorption lines with metal rich stars. This is the normalized spectrum, and I usually show in the plot spectra like that. So the shape of the continuum, the general shape of the spectrum is flattened and put to a value of 1 usually. And another effect is the stellar rotation, and this usually broadens the lines due to the Doppler effect. So why would we want to actually measure all these physical parameters? Well, there's a certain field in astronomy nowadays, very popular. It's called galactic archaeology. It's not quite something like this guy does, but still it's about understanding the history of our galaxy, the evolution of it, and how it all came to be to the shape that we observe today. So for doing galactic archaeology, it's very important to measure as many stars as possible, to measure their physical properties. And one way to do it is to look at their spectra. And for example, this is an example of fitting these observed spectra, which are in the black, with the black line, with stellar templates that we can produce from stellar models, so from physical models of stellar atmospheres. So if we can find a good match between the synthetic spectrum in red and the observed spectrum in black, then we can assume that the star has certain properties like certain temperature or gravity at the surface or the metallicity, so amount of heavier elements. But these are two very nice fits, but it's not always like that. So that's a hot star up there and a cooler star down here with other parameters more or less the same. But it's not always like that. So we don't have the synthetic spectra for all types of stars and for all types of physical conditions in the atmospheres or around stars. So I will talk mostly about, in terms of data, about two large spectroscopic surveys that as a mission, as a primary goal, have this galactic archaeology. So one is the Galah survey. It's conducted with a 4-meter telescope, so the size of the mirror is 4 meters in Australia. And the goal is to observe 1 million stars we want to measure, besides these basic stellar parameters, also a lot of abundances, so for different elements. And we have the data basically split into 4 wavelength ranges that are written here. And another mission is the Gaia ISO survey. Similarly, the goal is to do galactic archaeology, but in terms of selection functions, so which stars we observe, this one is also specifically dedicated to observe about 100 open clusters, so young groups of stars. And so the final output would be observations of about 100,000 stars, and it's also got a lot of wavelength ranges in which it observes. These are just the 3 that I list here. And this is conducted in Chile with an 8-meter telescope. So the size of the mirror is 8 meters. An example spectrum from the Galah survey looks like this, so the normalized spectrum. We see, of course, a lot of absorption lines from different elements in the atmosphere of a star. So this is a solar spectrum. But also we see a lot of features here, which are basically absorption lines due to our atmosphere, so the atmosphere of our planet. So we see immediately that not only the star contributes to the spectrum that we observe, but also our atmosphere, then the interstellar space, and so on. So there's that, and there's other things to consider when we want to, of course, measure properties of stars using the spectra. There's, of course, the evolutionary stages of a star, and if we go way back when a star is getting born, those are very turbulent times for a star, and it's difficult to put all that in our models to produce synthetic spectra that would, simulate simulate all those effects and all the environment around the star at that stage. Also, when the star is dying, there's many things happening there that is difficult to put into the synthetic templates. So in this context of this work, actually everything, all the spectra, all the observed spectra that cannot be well approximated with synthetic templates, we call those peculiar objects or peculiar spectra. So there's 2 types of peculiarities. There's the one that arise from the actual star, from the intrinsic properties of a star. And then there's those that creep in somewhere in the either observational or reduction phase. And we'll talk about this later. So just to give a few examples, this is the blue band in Galah and the red one. So we see, for example, emission. So emission lines instead of absorption lines is the hydrogen beta emission line, the hydrogen alpha emission line. These lines can be complex. This is an example from Gaia ISO survey. They can have multiple components in this emission profile. Then we've got different other issues. For example, this bump here in the continuum, this wavy shape, it's barely visible, but it's there. We've got these huge spikes in the infrared part of the Galah spectrum here, and other smaller features that you see. So these are all peculiarities that we want to account for in the end. And also the double lines in the spectrum, as you see here, these are due to collecting light from basically 2 stars, not just one in a single fiber. So this is also a kind of peculiarity in this context. So the question now could be, what happens if we don't account for these peculiarities, if we don't find them? Here's a plot of the measurement of several stellar parameters, so radial velocity of a star, then the effective temperature, gravity of the surface, metallicity, the rotation of the star, and one of the abundances, so this is the silicon. I wanted to show with these plots that how accurate we can get if we don't account for the peculiarities. So let's say that we have repeat observations of the same star. Let's say we have 5 spectra of the same star, and we compare how well we measure the parameters in all those 5 spectra. So ideally, you would get the same numbers from all 5 of them, because it's the same star that you observe. But of course, there's some scatter among these measurements, between these measurements. And the black points, they show the scatter for what we flag good, well-behaved normal stars. So the results that we trust. And then with the red points plotted, is this scatter plotted for repeated observations of peculiar stars. So we see with the average value of this scatter up here that basically all the values for the peculiar stars are larger. So that's one thing that happens. So the results in the end can be erroneous, can be questionable if we don't account for the peculiarities in the spectra. Of course, we can just flag them and tell the end user, okay, be careful when using these values, and that's already something that's useful. Another thing is that if we do find these peculiarities, this can actually be a source of further studies for these interesting objects, because some of them are really physically interesting. For example, chromospheric activity in stars manifests itself in the emission in otherwise absorption lines. So this is calcium absorption lines here. And we see they don't go down as they should in theory. There's more light in the core of the lines. So this is basically due to some emission happening in the upper layers of the atmosphere, so in the chromosphere of a star. And this is an indication for some sort of magnetic activity probably of the star. Some magnetic fields are putting some energy in those layers, and then we get emission out of that. Another example would be carbon-enhanced stars. It's something my colleague is working on. So usually in stars, there's a greater abundance of oxygen than carbon. But if it's not like that, if there's more carbon, we can get different carbon molecules. And they cause these wide absorption bands in the spectrum. And this is an example of a Galah spectrum, where actually all the parameters of these two stars are the same, except that one is carbon enhanced. So you see a lot of more features and absorption lines due to that. And the question here is whether this carbon comes from the interior of the star, whether it's somehow dredged up, or whether the star has been polluted by the environment around it. So it's an interesting study to do. Then we've got the emission that I showed in hydrogen beta or hydrogen alpha line that can produce different shapes of profiles. So for example, if we got some material flowing away from the star, so let's say stellar wind, we get a profile of an emission line like this. We call this a t-SNE profile. And this is usually what's happening when the star is dying or in some other evolutionary stages of a star. We also have the opposite effect, accretion. So material is flowing onto the star, onto the surface, which is also one of the situations when you have a star that's been born. And the profile then is inverse to the t-SNE. So these are all configurations of stars in their environment that are interesting to study by themselves. So if we can find them, then we can study them further. Another topic of interest would be binary stars. They are important in many ways. For one, they are important laboratories, important astrophysical tools for measuring mass and radius of a star. They are one of the only ways to explain different shapes of nebulae that we see in the sky. They can tell us about the evolution of single stars or of binary systems. They can help us by measuring distances across the universe and so on. So the question is now, okay, we have all these large data sets, and how do we handle the amount of data? Because you saw that we were measuring up to, let's say, 1 million spectra. Of course, it's difficult to go through them visually. But still, we say that people are visual beings, so astronomers should be as well. And if we give an astronomer some good visual interface to the data, then it's easier to apply the knowledge of an astronomer to actually extract information from the whole data set, even if it's millions and millions of spectra. And with this, we come to the dimensionality reduction and how this plays a role in what we want to do, so classification of stellar spectra. We can do classification basically in two ways. So either it's supervised classification or it's unsupervised. With the supervised classification, you have to have some model and you have to feed it some training set. So you have to have a good training set with good labels, the labels that you trust for your example spectra in this case. and you can apply this trained model to new data, of course, later. But this involves a lot of manual work, so it's exhausting in a way, and it can be biased, of course. Whereas with unsupervised classification, in other words, clustering, you can actually just put the data in without worrying about the labels, and then you can look at the results, and then applying your knowledge, you can decide what is what. Because this actually produces a visualization of the data, and it produces distinct groups that you can see by eye. So that's what we're doing in this case. And also, an important thing to note here is that with supervised classification, you're not really ready for the unexpected. So if something new happens in your data, you'll probably not see it if you don't use the unsupervised classification. Okay, so as I said, this unsupervised classification, so it's not based on a physical model. But it's useful. So it's something that I think should be used along with the physical models in any case. So what we expect from the dimensionality reduction of our data is that we want our data being projected from some space A. So this is the high dimensional space where each data point is a vector. In our case, a vector of flux values for each spectrum. And we want to project these data points into some low dimensional space B, so typically a two-dimensional map. By this, of course, we lose information, inevitably. But what we want from such a process is to preserve the important information, which is basically the structure of the feature space. So we imagine now that our data points lie on some low-dimensional feature space. So features like effective temperature, or gravity, or metallicity, or maybe emission lines, or whatever. These are all features. And we want to preserve the structure of that feature space also in the 2D map. So that's the goal of dimensionality reduction. And of course, there's many techniques that enable us to do that. This is just a short list of them. So we've been using a few of them already, but in the end, we have come across the t-SNE method that I will present to be the best one for this use case. So just to know that there are linear methods that do dimensionality reduction, and there are non-linear ones. So in a simple case of this plane folded in a Swiss roll already, very simple case, but the PCA as a linear method we see cannot really retrieve the underlying structure of the data. So all the points get mixed up, and we don't really see where's the beginning, where's the end of this curved plane. So it's not good for our case with intrinsically nonlinear data, such as spectra are. So there's many nonlinear methods to choose from. And as I mentioned, we kind of figured out that t-SNE is by far the best among them. And this was developed, this method was developed by van der Maat and Hinton in 2008. And it was later brought to our attention by one of our guys, Gal Matijevich, and used on the spectra from the RAVE survey. It stands for t-distributed stochastic neighbor embedding. So there were other methods called stochastic neighbor embedding before t-SNE. This is an improved version of those. So what basically t-SNE produces is a 2D visualization of our data. And so the data points that are similar to each other in this high dimensional space A should be close together in the space B, so in 2D map. That's what it does. And I'll show a few examples from the original paper just to demonstrate why t-SNE might be better than the other methods, the other nonlinear methods. So we see here a projection of digits, handwritten digits here. It's obvious, I believe, that t-SNE really separates the different classes of digits. So there's ones and sevens and zeros and whatever into these separate clusters of points. So this coloring is just to know that which figure is where, which digit is where. And so that's the global structure of the data. t-SNE is able to preserve the global as well as the local structure. That's an important aspect as well. So the local structure then would be what's happening inside each cluster. So let's say that we've got ones here, or sevens, and then as we go along the cluster, so up, down, or right, or left, or to right, or whatever, we see how the digit changes, so either its skewness, or its peculiar shape, or whatever. So that's the local structure of the data inside each cluster, and these whole clusters, they give us the global structure. Similar example is with these photos of different objects, but actually we put in photos of these objects from all possible angles. So we go around the object and take a photo of it. And so the t-SNE projection actually retrieves the structure of this data by saying, okay, each circle is one object, but as we go along the circle, around it, we actually look at photos that were taken from different angles. So the other methods, they come close, but they're not as effective as we see as t-SNE. To talk a little bit about the math, just shortly. So what we want, so as I said, is to have the similar points in space B being close together in space A, being close together also in space B, and the dissimilar points from space A to be far apart in space B. So we need some measure of similarity, in space A and space B. So if we can construct these two measures, then we can put them into a cost function, which is basically the Kullback-Leibler divergence written here, and we minimize this cost function. So we want that the similarity of two distinct points in space A to be as close as possible to the similarity of these same 2 points in space B. And then we put all this together and minimize the whole distribution. That's the idea, that's the objective. And so how we do these similarities in space A, we take a Gaussian. It's basically a probability distribution that some point AI in space A would call the point AJ, hey, you're my close neighbor. So that's the probability for that. And we use a sigma in this Gaussian distribution to be variable. Sigma varies depending on what we set as a perplexity parameter. So this is one of the input parameters to the t-SNE method. And it's basically an effective number of neighbors that you look for in this distribution. And we vary the sigma based on what the density of points in space A is. So for sparser regions in space A, so in this high-dimensional space, the sigma is greater. So we have the same number of neighbors for a certain point, as in the dense regions where the sigma will be smaller to have this same number of neighbors that we look at. Then in space B, we don't take the Gaussian, but we take the heavy-tailed student t distribution. So it's got heavier tails than the Gaussian. This is basically the improvement that t-SNE does over the previous versions of SNE. And it's also what solves the issue of crowding. So in all the other methods that you saw in the examples before, you saw that points are clustered sometimes very near the center of the map. So that's a crowding issue that most of these methods have. And t-SNE solves this issue by using this student t distribution. So these heavy tails of the student t function, they give more space to the points that would otherwise be very crowded up, and it's a lot of them to be in one place. And Gaussian would just crush them together in the center somewhere, and the student t distribution allows them to move more freely and have more space in the projection map. There's a nice web page to look at how t-SNE actually is doing all this and to understand more intuitively what it does, but I will not go into that. So you can look it up yourselves. And there's also a nice introduction to the whole t-SNE procedure by Kos et al. 2018, and of course in all the publications from the original author. So I will skip this, which is also on the website. So as we look at the publications made using t-SNE in science, so most of them are in computer science, or also medical and biomedical research. So astronomy also comes later somewhere in that list. It's growing, of course, over the years. These are some of the applications that have already been done with t-SNE, so in astronomy, but I will just skip those because I'm running out of time, as I saw. And I will tell you how we use this method to classify our spectra. So basically, there's a reduction pipeline in Galah that we have, and in the end, from the images that we take, we produce normalized spectra. But it's been lacking classification, so we have to do something about that. And for that, we need the t-SNE projection now. We need the cluster detection in the projection map, so in this space B. So density-based clustering, DB-scan was a good method of choice in this case because it detects any shape of clusters just according to their density. So if we want to automatically label our points in this projection map, this is a good way to do it. And we need a t-SNE Explorer, which is basically a web interface that allows us to do this elegantly. So the first results from this classification, or the t-SNE projection, we see here. So the color labeling is according to some parameters, so temperature, gravity, and metallicity here. We see a nice gradient of temperature across the whole map. This means that probably temperature is an important feature, or one of the most important features in spectra. And at first we took out the normal stars, which are outlined with this black line, and just do the projection again on the rest, which are the more peculiar examples of stars or of spectra, because this was due to the computational issues that we had at that time. And this is the new, so 3 times the size of the data set. This is the new projection made with t-SNE. And if I just present the Explorer a bit, so we have this projection map here. Okay, I'll skip to this. Okay, we have the projection map. It's split into hexagons for easier viewing. We click on a hexagon, we see the points inside. These are all colored based on the parameter that we choose here, and the color scale is up there. So it's a good way to quickly go through the whole data set just by clicking on hexagons and look at the separate spectra. So in the plots, we basically plot the median spectra for everything that's in the large hexagon. And the gray shaded area tells us the scatter of those spectra. And the black one is just an overplot of the spectrum that we choose here with the circled with the red line. And then we use the DB-scan with different modes to automatically select these islands of points in the map. So according to different modes of the DB-scan, we get different selections, of course, for these islands. And basically what we do then to do classification is to look, let's say, at this island. We examine the hexagons. We see that, okay, these are hot stars, metal poor ones. And we say, okay, we want to append the label to all these stars together. And so we select the right DB-scan mode that will select this whole island. And that's basically it. Okay, that's just how we do it technically. The classification in the end, so this was the first one, looked like that in the end. We've got 6 categories, just to go through them quickly. So we've got these cool stars there. These yellow snake-like shaped islands, they all actually correspond to some strong feature, which is this huge spike in the infrared, but it's always at some different wavelength. This was actually an issue that we had, and we had to figure out what's wrong with this, and we figured out that it's basically a piece of glass in the infrared arm of the spectroscope that's emitting some energetic particles, so this is what was causing these spikes. Again, a reduction issue here, so this wavy continuum, nothing physical, but just some error in the reduction process. Then we've got hot stars here, the metal poor and the metal rich ones, and a nice sequence of binaries down here in 2 islands. There's 2 islands of points because they're morphologically different, even if they're not physically different, not physically significant. But in one of the islands, the blue word component of the binary is stronger, and in the other, the red word component is stronger. So that's the whole distinction between these 2 islands. And we go along this shape. We go from more widely separated double lines to closer ones, which are almost blends in the end. And then when we have that classification, and we then get new data, we have the new data set, which is, let's say, 3 times as large, we can just apply the labels from before to this new data set, to this new projection. And okay, we see here all these binary stars, for example. We click on a hexagon, we see that, okay, some are already labeled because they're from the previous classification. And all the new ones are there, so they're probably also binary stars, but not labeled yet. So we again select the right DB-scan mode and just apply this flagging for binary stars to these 2 islands. And so on, and this is the new classification that we did just recently. Also including some new categories, like the carbon-enhanced stars here. And so this is a joint effort also in the sense that many people have to look actually at this to see their stars of interest in there, because one person cannot account for all the possible peculiarities that we have. To just mention the computational intensity. So, of course, this grows with the number of objects and also with the number of dimensions. And currently, with the code that we run in parallel on 48 cores, it's like a few hours, or let's say 5 or 6 hours for 300,000 objects with a dimensionality of, let's say, 15,000. So if we go to 1 million, this will be more than a day. So it's not really drastic anymore because of the issues that we solved with the computation. Just to show another example of a projection. So I've shown 600,000 stars before on that map, and I will be showing those that do not make it to the end of the reduction pipeline. That's also important because it's a lot of stars that we actually don't look at in the end, maybe. So we stop here before normalization and all these other processes. And this is a plot of 100 spectra. Most of them are noisy. Most of them is light just missing the fibers. There's also some dome flats in there. But there's also a significant number of actual spectra from stars. So this is an island, for example, of cool stars. There's one with H beta and H alpha in emission. A few of the islands like that. So this is the flat spectrum that I was talking about. It's interesting. So the signal is, of course, flat, but there's this one spike in the red arm that we're not sure yet what it's about. So it's good to also look at the stars that didn't make it through to the end in the reduction pipeline, because there might be something interesting or valuable in there. Just to show a few of the maps also for the Gaia ISO survey. So cool stars, H alpha emission. These double component profiles, so wider and the narrower component. Lithium-rich stars, and so on. And the reduction issues that is causing a lot of, no, it's not a reduction issue, but in these young clusters in the Gaia ISO, there's a lot of nebular emission present, of course, when we're looking at young clusters, and this causes these huge emission lines that we have to account for. They're not interesting in the scientific sense, so there's a huge issue with removing those lines. Okay, so because I'm running out of time, just a few more words. There's the parametric t-SNE method that we want to use, because then it learns the projection, and actually when you get the new data, it's immediately projected into the plane. You don't need the whole optimization part. And there's deep learning, of course, when we put t-SNE labels as the input information and get the actual probabilities for classes out. But it's difficult because there's many input parameters to put into this, and you need a very good quality training sample. There's the t-SNE in 3D. So if you've got some kind of a virtualization tool, so let's say helmets or glasses, you can actually put these projections in 3D, not in 2D. This way you retain more of the information from the data, and you can also, I don't know, zoom in or turn the projection with your hand, so it would be a nice feature. And it's something that our colleague in Villanova in the States is trying to do. And so these are my summary points. So the thing to emphasize is that I hope I have shown you that t-SNE Explorer, and with all the functionality, is a good tool to examine, to visualize the data and actually do the classification, or at least diagnose certain problems that you might have in a certain data set. And the point is also here that this method, of course, accepts all kinds of data. It's not just for stellar spectra. It can be anything, either in astronomy or in other fields of science. You just need a vector of values. And of course, we've got some ideas on how to improve the whole procedure for classification. So I'll finish here. Thank you.
Thank you very much, Gregor.
Thank you very much. Great talk. t-SNE is also very popular in single-cell biology.
As you've seen from those graphs.
Yeah, so where cells, they have a non-linear relation. And then t-SNE was a breakthrough, basically, to identify subpopulations of cells. So I just wonder, is there any way to extract features which drive clustering on the t-SNE? And if not, how do you explain why?
So to extract the features, is to see which features are important.
Yeah, like on the
So
PC you have loadings, you know exactly, if you see clustering, you know exactly which features drive the clustering. On t-SNE, this is, to my knowledge, impossible. So I'm asking everyone why.
I would say that if you use the parametric t-SNE, which basically uses some prescription to how to project data into the 2D space, with that you might get some information on the features from the from coefficients from those parameters, because that uses a deep learning or a neural network to do that. So, but in this the version of t-SNE that I showed, no, I guess you can't do it. But of course, you can always look at the data and see which features are important when you click for the different islands of points in the map. But otherwise, like you said, yeah, if you would use the parametric t-SNE, this would be possible, I would say. Because similarly as neural networks enable you to do that, if you got a neural network embedded with the t-SNE procedure, like in the parametric t-SNE, you could do that.
Not straightforward.
I don't have any experience yet with that, so I'm not sure.
Thank you.
I'm just interested, where do the spectra with the lowest signal to noise end up in a t-SNE distribution?
Yeah, that's a good question. So they usually end up in some separate island. So basically, with noisy spectra, you can have a similar a similar measure of similarity because of the properties of the Euclidean metric. So yeah, usually they're in a separate island. But I know we didn't really work specifically on that or to So I can say. Yes. Also, a very good question. Yeah. So in many islands, we see some spectra that just don't belong there. So they don't belong there because the Euclidean metric is not the perfect measure of similarity, of course, or of distance between the spectra. And for those who don't have the solution yet, I was playing with some other metrics. So there's the Manhattan, the Camber, and all the others. I was also trying to construct a new one that would actually solve this issue. You've got three spectra. So the black one, let's say, is the reference. This is just, let's say that this is a part of the spectrum. And you've got this feature in all the other two spectra, so in the black and the green, in the red and the green. And of course, the Euclidean distance between the red and black and the green and black will be the same. So this is what can happen. This is the contamination that can happen in these islands. So you get some spectrum that doesn't really belong there if you look at it visually, but of course the Euclidean distance to the other spectra was the same. I mean, was similar to all the other Euclidean distances in that space. So yeah, we don't have yet a solution for that. So there is some contamination, and these flags, of course, should be thought as conservative, but yeah, I hope we make progress on that.
A very interesting talk. You had a long list of different methods for dimensionality reduction. I couldn't see all the list, but I would just be interested in whether or not you test the autoencoder. So this deep network that, in a sense, also does some kind of dimensionality reduction.
I haven't tried that personally. I tried the LLE, for example, locally linear embedding, which also has a huge crowding issue. So in that respect, t-SNE performed much better. But these autoencoders are also implemented, I guess, in the parametric t-SNE version.
Okay.
So yeah, we want to try that. We have a new PhD student now that I think will get on to doing that. So yeah.
Thank you.
I had a question, actually.
Yeah.
Is it useful to try to fit, in a sense, the position in your projected map as a function of some physical quantity that you want to then recover from the spectrum? So I don't know, say the velocity difference of your double-line binary or something.
So we used to think that it's possible, But then when you think about t-SNE more, and especially if you go to that website where it's really nicely explained what t-SNE does, it's not really the case that you could do that. So basically, the closeness of points in the map is a measure of similarity, but it will not, there will not be a relation to the physical quantities or the features directly. So actually, the dimensions of the map, so the x and y axis, they don't mean anything. There's no physical sense in the dimensions.
So if you want to do feature measurement, then you should go back and use a different tool, effectively.
Yeah.
Yeah.
So this is basically useful for classification and for all kinds of morphological diversity that you can observe in there. But yeah, the actual to put out, let's say, numbers for features, it's difficult.
Okay, if there are no more questions, let's thank the speakers from this morning again.